Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to lecture number 38 on the subject of computer organization and assembly language programming. The title of today's session is bit shifting operations. Well, this slide shows today's agenda. As usual, the first few slides are a recap of x86-64 register set, programming toolchain, and instruction categories. Then we will study the shift and the rotate instructions, which shift the bits in the destination operand by one or more positions, either to the left or right. Well, for shift instructions, the bits shifted out are lost, while in rotate instructions, the bits shifted out from one end of the operand are put back into the other end. We'll also have a working demonstration of these instructions using the GNU GDB debugger. So, first a recap. This slide shows the register set of x86-64 microprocessor that we have discussed in length in lecture number 28 of this course. This slide summarizes the x86-64 programming toolchain and the layout of assembly program, and we have discussed this in detail in lecture number 29 and 30 of this course. If you have not gone through these sessions, I strongly recommend that you should first go through these sessions and then fall back to this. And finally, this slide shows the categories of x86-64 instructions that we are going to study in this course. We are done with the data transfer and arithmetic instructions, and we have also covered the logical instructions in the last session, and today we are going to talk about the bit shifting operations. Okay dear students, let us now start with our discussion on the first four shift instructions. Okay, the first instruction that we are going to discuss is the logical shift left or the arithmetic shift left instruction. This SHL or SAL perform the same operation, and that is shifts the bits in the destination to the left by count number of bits. And while doing so, a 0 is pushed into the least significant bit position, and the value in the most significant bit position is shifted into the carry flag. Well, both these instructions, SHL and SAL, are two operand instructions. The first operand is the destination operand and can be a register or a memory location. The second operand is the number of times we want to perform the shift operation. Well, dear students, some assemblers do not allow the immediate value to be greater than 1. So to have more than one shift operation in a single instruction, you can keep the value in the CL register. Since we are using NESM, which allows the immediate value to be greater than 1, so we may not be required to use the CL register anyways. And finally, for x86-64 processors, the maximum value you can give for this count is 63. The flags of our interest over here is the carry flag only, which contains the last most significant bit shifted out of the destination operand. Okay, so now consider these two assembly instructions. The 16-bit AX register contains a decimal value 5, and then we perform a left shift operation by 1. After the shift instruction executes, 0 is pushed from the least significant bit side. All the remaining bits are moved one position to the left, and this most significant bit, that is 0, is moved inside the carry flag. Do note the contents of the AX register is now 10. Previously it was 5. This one has moved on to this position and this one has moved on to this position. So this counts up to 10. So that is the previous contents of this AX register are multiplied by 2. 5 into 10, 2 is equal to 10. And this is what the usage of a left shift, that is, it is used to multiply the destination contents with 2 raised to the power n, where n is the number of bits shifted. And this applies to both unsigned numbers as well as signed numbers, of course stored in 2's complement. Okay dear students, now this slide shows the description of a logical shift right instruction, SHR. Well, it is quite similar to the shift left. Let me touch upon the differences only. Well, in case of a shift right, as is shown in this diagram, a 0 is pushed into the most significant bit position. All the bits are moved one position to the right, and this most significant bit moves out into the carry flag. And the most common use of a logical shift right instruction is to divide the unsigned destination contents with 2 raised to the power n, where n is the number of bits shifted. You can note that before the shift operation, the 16-bit AX register contains 33, and after the shift right by 1 operation has been performed, this value is divided by 2, so it becomes 16. Okay, so this slide shows the description of a shift arithmetic right instruction, SAR. And note the only difference in SAR is that it pushes the signed bit into the most significant bit position. Instead of 0, it pushes the signed bit into the most significant bit position, and therefore it can be used to divide the signed as well as the unsigned destination contents with 2 raised to the power n, where n is the number of bits shifted. Another important point to keep in mind is when dealing with negative numbers, as shown over here in this example. We have kept a -9 in AX and I have shifted right with the value with the count of 1. So once you perform a shift arithmetic right with negative number, the SAR instruction does not produce the same result as the IDIV instruction. The quotient from the IDIV instruction is rounded towards 0, while the result of the SAR instruction is rounded towards negative infinity. And this is what you can observe from the result. That is, once you divide -9 by 2, you actually get -4, but over here you are getting -5, because the IDIV instruction round the quotient towards 0, while the SAR instruction round the result towards negative infinity. Okay, I hope this is clear to you. Okay, so dear students, now is the time to move to our Linux terminal and see a working demonstration of these shift instructions. Let us move on to the terminal. Let me give the password, which of course I'm not going to tell you, and let me show you the code. Bit shift.nesum. Remember, you can download this program from the course Bitbucket repository. So here is the code, well documented. So instead of discussing it over here, let me assemble this and load it inside the GDB. NASM -G for debugging symbols, -FELF 64 for the output file format, bit shift.nasm, bit shift.o has been created. Let me link this bit shift.o and create the executable with the name of bit shift. And let me load this inside GDB in quiet mode, bit shift in text user interface. So great. Let me put a focus on the command window. Let me break at the symbol start. Let me see the registers by setting the layout to reds, and let me run. So this is the first instruction of our program, which moves a -1 inside the RAX register. Right now the RAX register contains 0. Let me execute this instruction by pressing SI. So now it contains -1. Well, over here I am trying to prove that the maximum immediate value or the maximum number of shifts you can perform is a 6-bit value. So the maximum value is 63. So it will perform a left shift with a value of 63, and all the shifts will be moved out, and finally only a single one can be observed over here. Let me execute this instruction, and here you go. So remember, the maximum number of shifts is limited to 63 on 64-bit architecture that we are using. And if you are executing these programs on a 32-bit processor, this value can be of a maximum of 5 bits, that is 31. Okay. So these instructions are going to prove now that the shift left or shift arithmetic left multiplies the number with 2 raised to the power n. So let me first zero out the RAX register. Let me set the carry flag. Observe, after the execution of STC instruction, the carry flag will be set. Now let me move a value 5 inside the RAX register. And now let me perform a shift left by 2 to the contents of RAX register. So this 5 will be multiplied by 2 raised to the power 2, that is 4, and the result will be 20. And of course the carry flag will contain the last bit shifted out, and that is of course 0, so it will contain 0. Once I execute this instruction, please do keep a track of the contents of RAX register as well as this carry flag. So there you go, you have a 20 over here and the carry flag contains 0. Once again, let me do a shift left with a signed number, but before, let me clear the contents of RAX by X or RAX. So the contents are cleared. Let me place a -7 over here. We have a -7. And now let me perform a left shift with a value or a count of 1. So this will be divided, or rather multiplied, and of course it contains now 14. The carry flag is set. Okay, after the shift left or shift arithmetic left, let me move on to the shift right, which divides an unsigned number with 2 raised to power n. And remember, this is SHR, that is a logical shift right. First, let me clear out the contents of RAX register. Set the carry flag. Observe, the carry flag is set. Let me move immediate value 40 decimal inside RAX over here. There you go. And now let me perform a logical shift right by 2 to the contents of RAX register. So this will divide the contents, that is 40 by 2 raised to power 2, that is 4, and you will get a 10 inside this RAX register. And of course the carry flag will contains the last bit shifted out, and that will be 0. And you can observe the contents of RAX as well as the E flag register. Okay, for a signed number, you need to use SAR instruction, and this is what is shown in these 3-4 instructions. 0 out the contents of RAX, set the carry flag, and now I'm moving minus 80 decimal inside RAX register. So RAX contains minus 80. Now I'm doing a shift arithmetic right operation on the contents of RAX with the value of 3. So this will divide this minus 80 with 2 raised to power 3, that is minus 8. So the result will be, of course, minus 10. Observe the contents. The result is minus 10. And of course the carry flag is cleared. Fine. And these instructions will show you that SAR does not produce the same result as IDIV. Remember, as I have previously said, that IDIV instruction rounds the result towards 0 for a negative number, of course, while this SAR instruction rounds the result, that is the quotient, towards negative infinity. So let me prove this to you. Clear out the contents of RAX. They are cleared. Let me place a minus 9 over here. So we have minus 9 inside RAX. Let me do shift arithmetic right to the contents of RAX with a value of 1. So instead of minus 4, you can observe that we will have a minus 5 over here. And similarly, if I perform a shift arithmetic right again on the contents of RAX with a value of 1, so it will be divided by 2. So instead of minus 4, you will get a minus 3. That is, the result is rounded towards negative infinity. And here you have minus 3 over here. And finally, of course, you know that these are the 3 instructions that make a call to the exit system call to gracefully exit the program. Let me press C to continue and press Q to quit. Let me fall back to the slides. Okay, dear students, let us move ahead and now let us study the 4 rotate instructions, which are quite similar to the shifts. The only difference is the bits re-enter from the opposite side as they leave. So the first instruction we are going to study is the rotate left, ROL. It is also a 2-operand instruction. The first operand is the destination operand and can be a register or a memory location. The second operand is the number of times we want to perform the rotate operation, which again for x86-64 can be a 6-bit value, that is a maximum of 63. Well, difference in rotate left, the most significant bit over here is placed into the carry flag as well as pushed back into the register at the least significant bit side, and the remaining bits are moved 1 position to the left. And this is the code snippet that shows an example of rotate left. The AL register contains this 8-bit binary value, and we are performing our rotate left instruction to the contents of AL register with the value of 1. Note, after the ROL instruction, the most significant bit, which is 1 over here, is removed and pushed in from the left. This one is pushed from the left. So this one has moved over here and the remaining all bits are shifted to the left. And of course, this one, that is the most significant bit, other than being pushed over here, it is also placed inside the carry flag. And this is what has been shown over here. The use of these rotate instruction is to bit the shifts across multiple words. Now, let me talk about a variant of rotate left instruction, that is rotate carry left, RCL. It is similar to rotate left. The only difference is that instead of this 64-bit register, it works like a 65-bit register with the carry flag as the most significant bit. So the previous value of the carry flag is shifted into the least significant bit side. The most significant bit is pushed into the carry flag, and all the remaining bits are moved one position to the left. And this is the code snippet that describes this process. This CLC instruction, of course, clears the carry flag, that is CF contains 0. So this CF contains 0. This move instruction places 88 hex value inside the 8-bit AL register. The binary contents are also shown. This rotate carry left performs the rotate through carry operation on the AL register with an immediate value or a count of 1. So this RCL instruction pushes the 0 inside this carry flag from the left. That is, the 0 inside the carry flag is pushed over here. So this 0 inside the carry flag is pushed from the left. So you can observe, instead of 3 zeros, we have 4 zeros over here. All the bits are shifted one position to the left. And this most significant bit inside the AL register is placed inside the carry flag. So after this operation is done, carry flag contains 1. And this is what is shown over here. And this second RCL instruction pushes this carry flag now contains 1. This 1 is pushed from the least significant bit side. So this 1 is pushed over here. You can note we have a 1 over here, and then 1, 2, 3, 4, and then we have 4 zeros. All the bits are shifted one position to the left, and the most significant bit, which is a 0 over here, is placed inside the carry flag. I think this makes sense to you all. If still this is not clear, please re-listen this part of the video to have a clear concept about how the rotate through carry left instruction works. Okay, so done with the left, moving towards the right. So rotate right, ROR instruction. This slide describes the rotate right instruction. This rotate right instruction is similar to rotate left. The only difference is over here the bits are shifted to the right. And this code snippet describes the process. I hope this makes sense to you all. The AL contains these 8-bit values. Rotate right rotates the contents of AL by 1. So whatever is there in the least significant bit side is pushed from this side and also placed inside the carry flag. So you can observe that this 0 is taken up from here and pushed from this side. So rest all the shifts are moved towards right, and this least significant bit 0 is also placed inside the carry flag. So that's great. And finally, this slide describes the rotate through carry right, RCR, which is similar to rotate through carry left, with the difference that over here the bits are shifted to the right, and of course through the carry flag. Over here again, the 64-bit destination register, or maybe the memory, works as if it is a 65-bit register with the carry flag on the least significant bit side. And this is the code snippet that describes the entire process. This STC instruction sets the carry flag. move AL comma 10 hex, places a 10 hex value inside the AL register shown in binary over here, 1 and this 0. And once you perform a RCR, rotate through carry right to the contents of the AL register, the previous contents of the carry flag, this contains 1, are pushed from the most significant bit side. So this carry flag contains 1, this is moved from this side, so you can note that after the RCR instruction execute, we have a 1 over here. Rest all the instructions have moved 1 position to the right. And over here the least significant bit is moved inside the carry flag. The least significant bit side is moved inside the carry flag. That is great. Okay, my dear students, for a crystal clear understanding about these 4 rotate instructions, please do download this bitrotate.nasm file from class Bitbucket repository and execute it using the GDB debugger. I am leaving this task on to you and I hope you will do it. So that is all for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.